In today's video, we are going to talk about Schrodinger's wave equation. The Schrodinger wave equation is like Newton's law in classical mechanics. Newton's law described the behavior of a dynamic system, and in the same way, Schrodinger's equation described the behavior of quantum mechanics. It is used to find the allowed energies of a quantum mechanical system and the associated wave function that gives a probability of finding the particle at a certain position. It is important to note that Schrodinger's equation cannot be derived from any underlying physics principle. It is a statement of how physics works and can be viewed as a postulate. In today's video, we are going to talk about how this equation is motivated. Let's start with the general plane wave equation and solution. Our general solution will be A equals A naught cos kx minus omega t. Let us now differentiate our solution with respect to x, and then differentiate again, so we obtain d squared a by dx squared. We therefore obtain minus k squared a. We shall now differentiate our solution, but this time with respect to time, and also differentiate again so that we can find d squared a by dt squared. And doing this will give us minus omega squared a. Subbing this back into our plane wave equation gives us minus k squared equals minus omega squared over v squared, and therefore omega equals v times the magnitude of k. Subbing in our equation for omega into our equation for energy gives us E equals h bar v k. We know that momentum P equals h bar k. Therefore, our energy E will equal to PV, which is the energy of a photon. We can see that this doesn't agree with our equation for energy of a classical particle, which is p squared over 2m. To be able to satisfy both the equations, I will try and look at the relationship between energy and omega and energy and k. We can see that the energy is proportional to omega, whereas in the other case the energy is proportional to k squared. This means that we differentiate twice with respect to x, but only once with respect to time. Let us now consider the equation d squared a over dx squared equals alpha dA over dt. With this being our general solution and differentiating twice with respect to x gives us minus k squared a, and differentiating once with respect to time gives us minus I omega a. And plugging this back into our equation gives us k squared equals I alpha omega. Since E equals h bar omega, which is equal to p squared over 2m, rearranging for p squared gives us 2m h bar omega. And since p equals h bar k, we then obtain h bar squared k squared equals 2m h bar k. Rearranging for k squared gives us this equation. And subbing this into our alpha equation gives us alpha equals 2m over I h bar. We then plug in our alpha back into the equation we considered earlier. Multiplying both sides by minus h bar squared over 2m gives us our Schrodinger's equation for a free particle, with psi being our solution to the equation, which is a wave function. Finding deep psi by dt and deep psi squared by dx squared gives us this equation. H bar omega is the energy equation, which we will call E total, and h bar squared k squared over 2m is our kinetic energy equation, which means that this equation applies to a free particle with zero potential. To obtain a more general solution for a particle with kinetic and potential energy, we will write the total energy as being equal to the kinetic plus the potential energy of the particle. Adding on our potential term to our free particle equation, we arrive at our time-dependent Schrodinger equation. The solutions in one dimension for the time-dependent Schrodinger equation are waves in space and time, and describe the quantum behavior of a particle. The solution to this equation is called wave function, which is psi. It can be used to predict the probability of position of particle. For example, in Young's double-slit experiment, if you fire an electron one by one, the particle shows up more likely in certain regions than others. Schrödinger's equation can also be used to predict the position of electrons, where some are more likely to occur in certain regions than others. In addition, it can also be used to predict the shape of orbitals. So, as you can see, Schrödinger's equation has many applications and plays a very important part in quantum mechanics.